Hello everybody, and welcome back to the second video in a series of review topics covering common conservation equations used in mechanical engineering. I am Professor Matt Anderson, and I'm glad that you're interested in this video, as I'll take that as confirmation that the first video was informative. Again, please keep in mind that these videos were developed as a refresher for your thermal science conservation equations. As these topics were previously introduced in your core ME courses, these videos are not intended to be a complete introduction to the principles that were previously presented and derived in those core classes. This second video covers conservation of energy, also referred to as energy balance. So without any further ado, let's jump right in. So just like our first video, when we're looking at conservation of mass in both a lumped equation form as well as integral equation form, we're going to do the exact same thing for conservation of energy. So we're assuming that energy can neither be created nor destroyed, it can only change forms. So our equation that we're going to look at is our energy balance equations. Just like we did last time, shorthand for my notes and example problems, I will write these as our energy balance. All right. And just like we looked at last time, we need to have a control volume that we're analyzing, right? So we need to have something specific that we're looking at such that we can account for this energy. So let's draw an example, and we will keep adding to it as we look at the different terms in the governing equation. So let's just say that we're going to have some sort of engineering device that looks something like this. We need to define the boundaries, or the difference between the internal, the control volume, as well as the surroundings, and we do that with a red dashed line. In this case, it's more of a pink dashed line, right? So that is going to be our control volume that we're looking at analyzing. And let's start, just like we did the first time, with our lumped analysis. So if we take a look at our governing equation, and I apologize, it's probably a little small, what we're going to do here is we're going to look at each of these terms individually and apply them to our system that we're interested in. So let's start with the first term on the left-hand side. This is our transient term. This is the time rate of change of energy within our control volume, right, inside of this, and how that changes. If we're looking at a steady state phenomena or a steady state analysis, that term goes away. If we're not, if there's transient portions of this, we have to account for that. So let's take a look at the term, right? So again, I want to review capital E, or capital any letter in this equation, is going to be an extensive property. So it's a function of the system size, or the control volume size. The larger this control volume, the more energy associated with that. Energy, we know, can have various forms. In our thermal analysis, we have accounted for internal energy plus potential energy plus kinetic energy. And that's as a function of the control volume here that we're looking at. So if I want to do, again, just for completeness, write this in terms of our total energy is equal to our mass specific, so our intensive energy, and we multiply that by the mass of the system. Or we can say that's equal to m times our mass specific internal energy, our mass specific potential energy, plus our mass specific kinetic energy. So all that is our transient term on the left-hand side of the equation. Now, if we move to the right-hand side of the equation, the first two terms on the right-hand side are our energy transfer as it crosses our system boundary. But now this is energy transfer not in terms of a mass crossing our system boundary, right, but in terms of any sort of heat transfer or work transfer as it crosses our system boundary. So let's blow these values up a little bit, and now we can see that we can have Q dot, so a rate basis of energy transfer via heat transfer, and W dot, right, which is a rate basis of work as that crosses our system boundaries. So we can, if we take a look at this example here, we could have some amount of heat transfer, and if we recall from our heat transfer, that could take the form of conduction, convection, or radiation into our system, or that heat transfer could be out of our system, again via conduction, convection, or radiation. So we have a sign convention we're going to have to keep track of, and we'll get to that in just one second. We also can have work transfer. Work transfer is organized energy transfer. We can think of this as a paddle wheel, some sort of shaft power that's crossing our system boundary. that's either extracting or inputting energy into that control volume, or it can take the form of electrons through a wire, right, current. And so we can account for that energy transfer. I'm going to draw, for the sake of our example, we're mechanical engineers instead of electrical engineers. We have some paddle wheel that is rotating, right, and we're putting work into our system or our control volume because of that. So a couple of things to highlight, right? We commonly employ a consistent sign convention when it comes to heat transfer and work transfer. And so positive heat transfer, and on a rate basis, that's what the dot stands for, right? Heat transfer is positive into the control volume. Work transfer term is positive when it's out of the control volume. If our system here, our engine, our device here is outputting work, we think of that as positive. The way I remember this, engineers commonly think of engines as good things, right? So an engine works via putting in heat transfer, Q dot into the system is positive, and we get work out of the system. W dot out of the system is a positive, right? So according to our sign convention, that's what we need to keep track of. The final two terms, these two summation terms in our energy balance equation here, account for any sort of energy that's coming into our system or our control volume or leaving our control volume due to mass crossing those system boundaries. So let's just say, for the case of this example here, we have mass coming in at location 1, mass coming in at location 2, and it's leaving at location 3. Right? Now we have to account for that energy that's crossing with that mass. So if we blow up these terms, and I highlighted both of them, but then brought them into just one term that made it large enough that we could see it. So what we do now is we take the mass flow rate, m dot, which we talked about in the mass conservation equation, and we have to multiply that by various forms of mass-specific energy, right? And so those different terms are going to be H. H is our enthalpy. And so enthalpy is a combination of internal energy plus PV, right? I think of this, or I explain this as flow work. We have to put some amount of energy to push that fluid across a system boundary, a control surface. And so now that's accounting for that work that's required. So enthalpy is a combination of internal energy as well as the flow work, or the energy that's required to cross that system boundary, right? Our V squared over 2 term, that's our kinetic energy, our mass-specific kinetic energy. And then our GZ is our potential energy due to elevation, right? So if our control volume's really tall, we have to account for those changes. The last thing to bring up with this is that we have to account for this both on the mass, the fluid coming in, as well as the fluid coming out. So both of these summation terms, they just have a different sign convention in front of them, but we're accounting for both. We have to add up all of the terms of the mass flow coming in, as well as the mass flow leaving, and we multiply that by its mass-specific energy. Moving on to our integral relationship for our conservation of energy, or our energy balance, it's going to look very similar. The terms are very similar. Now we just have integral relations for integrating the entire control volume as well as our control surface to account for those fluxes of energy crossing. So adding the equation here, left-hand side of this equation, we've just moved things around just a little bit here. Left-hand side, again, is our rate basis of heat transfer and work transfer as it crosses our system boundaries. Our sign convention is the exact same. We just now have to account for that just like we previously did within the lumped capacity. Now, the first term on the right-hand side of this equation is a time rate of change of an integral over that entire control volume. So we're taking all of that energy, that mass-specific energy, if you notice that lowercase e, and then we have to multiply it by density as well as integrate over that volume. That's going to give us a total energy, and we take the time rate of change of that. So that is our time rate of change of energy within our control volume. The last term on the right-hand side here, that is exactly like we talked about in the mass conservation equation, right? We have that dot product of our normal vector and our velocity vector. That allows us to combine both our mass flow rate into and out of our control volume into one term. When we integrate around that entire boundary, right, what we call our control surface, we then account for all of our inflows as well as outflows and the associated energy that's crossing with that mass that's crossing our system boundaries. So I'm not going to add much to this here. Just note that this is a more universal equation, right? It's not lumped. We can have properties that vary throughout our system as well as on our control surface, right? It's allowed to vary. We just have to account for those variations by integrating over those areas or over that volume. After reviewing our conservation of mass equations, you can see that our conservation of energy equations are very similar, right? Both in a lumped sense as well as on an integral sense. So the review topics that were covered in our conservation of mass review apply to this conservation of energy as well. With that, I am going to conclude this review of the conservation of energy. Hopefully you found this useful, and as always, if you have any questions, please feel free to reach out to either myself or your TA.